Welcome back. We're going to continue with Unit 2, Chapter 5, Polynomials and Polynomial Equations. Our goals for today, our targets for this lesson, will be to determine whether or not an equation is a polynomial and write it in standard form. Use synthetic substitution to evaluate a polynomial function for a given value. Describe the end behavior of a graph of a polynomial function. And finally, graph a polynomial function with the assistance of a graphing calculator. So if you have your graphing calculators with you at home, it'd be a good time to get them out and practice. So you have these copied down in your notes for section 5.2 as you'll be turning your notes in or having them checked in class tomorrow. So section 5.2, the title of it in your textbook is Evaluating and Graphing Polynomial Functions. This information that you see here is from a chart on page 337. So if you have your book with you, either online or if you have your actual textbook, you might want to get that out and look at that page. If you want to copy from there, it's very similar information to what I'm going to be filling in the chart. So some definitions of various polynomial functions. First of all, degree 0, it's called a constant function. You can write it in standard form as f of x equals a times x to the 0, or f of x equals a. Basically, there is no variable in the equation other than y equals x equals a number. So there's no variables on the right side of the equation, so to speak. No x squareds, no x cubes, no x's. It's just y equals 3, y equals 4. So my example here is y equals 3. That's a constant function. That will be a horizontal line. You've seen those before. The second type of polynomial function you'll see has a degree of 1. So an x to the first power is the highest power you'll see, so to speak. It's called a linear function. Standard form is f of x equals a times x plus b, or a times x to the first power. You don't really need the first power there. I put it there just so you can see that it's there. But normally it's hidden. It just says a times x plus b. An example of this, f of x equals 4x minus 2. This is also line. Constant functions are lines. Linear functions are lines. The difference is linear functions will be slanted lines. They'll either be angling up from left to right or down from left to right, whereas constant functions are horizontal all the way there. That's why they're called constants. They don't go up, they don't go down. So we've seen those before. We've seen, from last chapter, we've seen the third one, less quadratic. That's a degree of 2. That means there's an x squared in your equation. Standard form, f of x equals ax squared plus bx plus c. An example I gave is f of x equals 4x squared plus 6x minus 7. I know if you're saying, what is this f of x? Look up here what I did here. I wrote y equals 3. I could have easily written f of x equals 3. F of x is the same thing as y. We just call that function notation. F of x and the y, they are the same. They're the same thing. So if you see f of x, it just means y. It's giving the function a name. You can see g of x, h of x. Q of x, you see all different types of naming the functions that way. It's like how they name hurricanes. So, say this hurricane or that hurricane. It's a way to name different functions. So when you graph them, or look at them algebraically, you can differentiate between various equations. 3, cubic functions. Cubic functions have a degree of 3. So in other words, you're going to see power of 3 somewhere in your equation. In standard form, it says f of x equals a times x to the third plus bx squared plus cx plus d, where a, b, c, and d are just real numbers. F of x equals 3x cubed plus 2x squared plus 5x minus 7. Now, to be a cubic, we don't need to have the x squared or the x or even the constant, the d, but you do need an x to the third power. So if it was just f of x equals 3x to the third, that would also be a cubic function. We look at what the highest power is. The highest power is what we call the degree. In a degree 4, or highest power of 4, we call that a quartic. F of x equals ax to the 4th plus bx to the third plus cx squared plus dx plus, that's an e down there. And an example I gave is to verify the point I just made in the previous statement, f of x equals x to the fourth plus 6x plus 10. Notice there's no x to the third or x squared, but we do have the highest power of x to the fourth. Okay? Whatever the highest power is, that's what we name it. Just because there's a 6x there, we don't say, well, that's linear because there's a linear piece. No, it's whatever the highest exponent is. Once we get past fourth power, the fourth power, fifth power, sixth power, we just call them polynomials. So there is no special name for fifth power or sixth power polynomials that we're going to worry about, just through fourth power. And generally, it's going to be constant, linear, quadratic, and cubics that we deal with on the most in this class, but you will see quartics as well. Okay, one last reminder, I have written up here, highest power, that's what the degree is. The degree is the highest power in a polynomial. So that's how we name it. So highest power out of all of them. Even if it's not in order from highest to lowest, whatever the highest power is, that's what the degree would be. For the following examples, I'm going to ask you to do a few things. Okay, I'm going to give you an equation. I want you, number one, tell me, is it a polynomial or not? If it is, name the type of polynomial. If it isn't, then tell me why it's not. Also, with the polynomial in standard form means highest power, highest degree, highest power to lowest power. So that's what I need you to do for each of these problems. Highest to lowest power, that's standard form. The degree, remember, that's the biggest exponent. We talked about that in the last slide. Biggest exponent. And the type. Is it a constant? Is it a quartic? Is it a cubic? Is it a quadratic equation? So that's what we're going to do. Also name the leading coefficient, the LC. That is the first coefficient in standard form. In standard form. And the constant term is the term or number without an exponent, without, excuse me, a variable. Without a variable. Oops. A variable. Okay, so we're going to identify these from each piece. F of x equals 4x squared minus 3x to the first plus 4x to the fourth minus 8. Is it a polynomial? Well, it's a polynomial because I have all integer exponents. Positive integer exponents, so counting numbers. 0 and above. No decimals, no fractions, no irrational numbers, or exponents. We don't have any negative exponents, or exponents that were in the denominator, which would be negative exponents if I rewrote them using the negative exponent rule. So this is a polynomial. It fits that definition. Let's use black. So yes, it's a polynomial. Okay. Standard form, it is not in standard form as is, so standard form, we're going to rewrite that. And what we do is we look for the term with the biggest power. The biggest power in this one is 4. So 4x to the fourth goes first. The next biggest is this 2 here. So plus 4x squared. And then we have a negative 3x to the 1, so negative 3x minus 8. This would be standard form. Highest power down to the constant. That's what standard form is. Now, our constant. The only term without a variable is the negative 8. So our constant is negative 8. Our leading coefficient. Let's see if I can't move this down a little bit. Our leading coefficient. Now we have it in standard form. It would be that 4 right there. So our leading coefficient is the number in front of the highest power of x, which is 4. And those are all in the type. I almost forgot. What type is it? Well, as long we can name it as long as the degree is 4 or less. It's a degree of 4. So it is a quartic. And I don't think we actually said the degree, but our degree is 4. The highest power is 4. So that's how we determine if something is a polynomial or not, how we write it in standard form, what the constant term is, what the leading coefficient term is, how we determine the type. It is from the degree. You really have to know the degree before you can name what type it is. So we're going to go through the rest of these examples. Feel free, as we go through these, to pause and see what you think, okay, as we go through these examples. First one, f of x equals 3x to the 4th plus 2x to the minus 2 plus 6. Is this a polynomial? Okay. It's not a polynomial. Why is it not a polynomial? It's not a polynomial because we have a negative exponent. This x to the negative 2 right here. 2x to the negative 2. That's the term that made it not a polynomial. If it's not a polynomial, we don't have to do the rest of the stuff. We don't have to put it in standard form. So it isn't 1 if it's not a polynomial. We don't have to do what type because it's not even a polynomial. So we don't have to do the rest of the stuff. So you're thinking, oh boy, all of these are not polynomials. Maybe we'll be lucky and it'll be that way. Let's try number 3. When you're ready to keep going with me, go ahead and push play again. 2x to the 1/2 plus 3x squared plus 2x plus 4. Is this a polynomial? And the answer is not a polynomial. And the reason it's not a polynomial is this term right here. 2x to the 1/2. We cannot have fractions or roots in our exponents or decimals, okay, or negative numbers. If it's any of those, it's not a polynomial. So that's another one, not a polynomial. You try this last one. Tell me if it is or is not. Unfortunately, if you like having an easier problem, or I should say less to right, this is a polynomial. So, why is it a polynomial? I have a constant term. I have one variable term. The variable term has a positive 1 as the exponent. I'm good to go. It's a polynomial. So, is it in standard form? It's not as we see, as it's shown here, so we have to reorder it. The highest power is the x the first, so we're going to write negative 2x first plus 13. Yes, that negative 2 goes with the 2x because it's to the left of it. So that's what it would look like in standard form. The degree we just kind of talked about, that is 1. It's 2x to the first power, so degree is 1. The type, well, if it has a degree of 1, that's a linear function. And the leading coefficient, now that we have it in standard form, is negative 2. The constant is plus or positive 13. So to determine whether something is or is not a polynomial, and it's also how we define all the pieces, find the ways to describe it, how to determine what the degree is, what type it is, what the leading coefficient, and the constant. So those are all parts of a polynomial, or ways to describe a polynomial. Okay, direct substitution. Direct substitution is a method for evaluating a value of a specific numeric value to be plugged into an equation. In other words, you're plugging a number in for a variable. So direct substitution, basically, f of x equals negative 3x plus x squared minus 12x minus 5. That's the equation. it would say evaluate when x equals, let's say, 2. So if I'm doing this by hand, I would put 2 in for x. So f, or the function value of 2, or the function value when x is 2, that's what this f of 2 means, is f parentheses 2. It's not f times 2. It's saying I'm plugging 2 in for x. So I'm going to do that. I'm going to put it in parentheses. If I'm doing it by hand, I'm doing order of operations. So I go through and I say, please excuse my dear Aunt Sally. The parentheses are 2 and 2. They're the only things inside. But I do have exponents, which would be the e. So 2 to the third power is 2 times 2 times 2, which is 8. Right? And 2 to the second power is 4. Minus 12 times 2, minus 5. So my, that's multiply. 3 times 8, or negative 3 times 8 is negative 24, plus 4. Minus 12 times 2 is negative 24, minus 5. Now we're down to addition and subtraction. We just go left to right for that. We get negative 24 plus 4, that's negative 20, minus 24 minus 5. Negative 20 minus 24 is negative 44 minus 5, and negative 44 minus 5 is negative 49. Now obviously, that's just a refresher of order of operations. You could just put it in your calculator to double check. We're going to do that in the next one, but feel free to pause and put this in your calculator to see if you get negative 49. On this one, I'm going to show you how we can use the graphing calculator a couple of ways. Okay? One, just plugging it in your calculator. 2, showing how we can use the graph and some values or functions on the graphing part to evaluate. So let's evaluate this one. X equals 4 this time. So it's going to look something like this when we plug it in. F, the function value of 4, is 4 cubed minus 5 times 4 squared plus 6 times 4 plus 1. So we can put it into y equals. We can put the equation x cubed, or f of x equals x cubed minus 5x squared plus 6x plus 1 in our calculator. So bring your calculator up, or y equals, and clear out whatever I had in there from before. X to the third power minus 5x squared plus 6x plus 1. So we're putting it in with the variables and y equals. Okay. If I hit second and I hit trace, trace right here. Oops, I must hit trace. I didn't want seconds. Trace. And I'm going to use the value of 1. Hit enter. We've done this before. I put in number 4. I get 9. So from the calculator, it says when x is 4 for this equation, I get 9. I also can just, on my calculator, go to the regular screen, type in parentheses, or plug in 4 cubed, minus 5 times 4 squared, plus 6 times 4 plus 1. I can just plug that in and I get the same value. So those are 2 ways to do it in your graphing calculator. So to refresh your memory on the second trace option. Okay, so to do it by hand, the old-fashioned way that I was forced to do it, like in example 1 here, or the new ways of technology that you are all lucky enough to have the opportunity to use. So the previous method, direct substitution, we've done that before. That's how you've always evaluated polynomials for a certain value of x. I'm going to show you a different method called synthetic substitution. And you're going to say, why are we doing this, Mr. Cohen? And you'll see. It's practice for something you're going to need down the road when we divide polynomials. Okay? But for right now, it's just a practice of the system we have. So In synthetic substitution, what you do is you make this kind of upside down box or a big long L at the bottom. We take all the coefficients and we put them in the box. So 5x to the third, negative 3x squared, negative 3 comes next. Negative x to the first, so negative 1. We don't put x. Coefficients now, remember the numbers in front, plus 7. I want to check also when I'm looking at whatever my degree is, if there's a gap, I have to put a 0 in this line right here. I have to put a 0 so wherever the gap is. So make sure that if there's gaps, and we'll do some problems where there are some gaps, you'll see what I mean by that. Okay, but just keep that in mind. This one, it hit every power from 3 all the way down to the constant, or 0. So we put that out there, and then whatever value we're trying to evaluate, in this case it's 2, that goes to the left of that vertical line. This is how it starts. Okay, it's going to be pretty cool. Might be kind of confusing the first time, but you practice it, you'll get it eventually, I promise. We bring that 5 down, and now what we do is we say, okay, we're going to multiply everything at the bottom by that number on the outside. So 5 times 2, that's 10. And notice that goes inside the box under the next term to the right. So in this case, negative 3. We are going to add vertically in these inside the box. So negative 3 plus 10 is positive 7. And now we do it again. 7 times 2 is 14. Goes to the right of 10. Underneath the negative 1. Negative 1 plus 14 is 13. Do it again. 13 times 2 is 26. 7 plus 26 is 33. So the function value of 2 is 33. Okay, rewind that. If you didn't get it, rewind it, go back to it. Okay, I'm going to check it now on our calculator real fast. 5 times 2 to the third power minus 3 times 2 squared minus 2 plus 7. Let's see what we get. Let's see what we get. We get 33, which is exactly what we got using synthetic substitution. I'd like you guys to try this one. Okay, rewind that if you need to see it again, read the last one, and see if you can set it up. And I'll have to give you a second after we set it up correctly, and then try the problem. Okay, so take a moment to see if you can set it up first. Okay, so hopefully you tried setting this up on your own. Coefficient, we have negative 2x to the fourth power, so negative 2 is the first coefficient. Negative 1x to the third, negative 1x to the third. Notice we go straight to x. What power is missing here? 4, 3, x, negative 5. We are missing a x squared term. There really should be a 0x squared term here. So inside of the box, I'm going to put a 0. And that's what I meant previously when I said when you skip a term, so to speak, in the equation, you have to replace it with a 0 inside of the box on your top line for synthetic substitution. 4, negative 5, nothing else is skipped. Negative 1 goes outside. So check and see, did you set it up correctly? Hopefully it makes sense now. It's supposed to be set up. From here, I'm going to pause it and let you go ahead and try this problem on your own. Okay, so at this point, we start out the same way. We bring that first term straight down, and the number at the bottom is going to get multiplied by this number on the outside. So negative 2 times negative 1 makes that positive 2. Remember, we add on the inside. Negative 1 plus 2 is 1. 1 times negative 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times negative 1 is positive 1. 4 plus 1 is 5. Add 4 and 1. 5 times negative 1 is a negative 5. Negative 5 minus 5 is negative 10. Whatever this last number is, that's our answer. So G of negative 1 is negative 10. Once again, you can plug in your calculator, check it, plug in negative 1 in the equation. I'll let you try that the same way we plugged it in our calculator for the last problem. So the same way we did with this. Try, plug it in, verify you get the same answer. Make sure you use parentheses when you put the number in for X. our last concept for today is what we call end behavior. End behavior is not, when you think of a behavior report on your report card, were you doing well? Did you listen to your teacher? Were you cooperative? Or were you bad behavior, disrupting class, out of your seat, being disrespectful, et cetera, et cetera. That's not the behavior we're really looking for. We're not going to say this graph was disrespectful. They can't be disrespectful. So what it can do is we can describe how it behaves as it goes on and on forever and ever and ever. That's why we call it end behavior. As we go to the right or as we go to the left. So we're going to look at this behavior or this graph and we're going to say, does the graph go up, get bigger, or does the graph go down, get smaller as we go right or left? That's what this means. Okay? So as x, this first one right here, this notation, x, arrow, and this is infinity, okay? Infinity. And this is negative infinity. That's what these terms represent, the sideways 8. So as x arrow infinity means, what does it mean in English? As x approaches positive infinity to infinity, or as x goes to the right. These are the ways I want you to think about it, whatever makes more sense to you. As x goes to the right. And this one, x arrow negative infinity, means as x approaches negative infinity, or as x goes to the left. That's what those phrases mean. As x arrow positive sideways 8 or x sideways infinity is as x goes to the right. That's really what it boils down to. X arrow negative infinity means as x goes to the left. So that's what these questions, as the value of x gets bigger, when it goes to the right, x is getting bigger, okay, what happens to the graph? Is it going up or is it going down? So here's how we would answer this question. Let's bring this graph down here. Oops. Let's bring the whole thing. Okay, we got it down here where we have a little more room. So here's our function, f of x. Let's use the red marker. As f of x, excuse me, rewrite that. As x approaches positive infinity. I don't even need the as in there, it's just implied. So I'm going to take that away because you probably won't see that. Okay? F of x does what? What does f of x do? F of x is the graph. Okay? If we trace this graph, it's making a U shape, right? So if we start at the origin and we start going to the right, as x goes to the right from the origin, my graph is going kind of up and to the right, but the general direction is up. So as we go to the right, our graph is going up. Going up, is that positive or negative infinity, do you think? Going up would be positive infinity. Okay? And I probably should have had a positive infinity by this one as x goes to the right. Now, we have another direction. That's the first one. Second, as x approaches negative infinity, as x goes to the left this time, what happens to the function? So here we are. We're going to go to the left and kind of trace this, and our graph is going up again. So if we're going up again, then what is f of x doing? F of x is approaching positive or negative infinity. It's approaching positive infinity. So that's what end behavior is doing. This positive and negative infinity is basically saying as our variable gets bigger when we plug in this case x, as x gets bigger as we plug it in, the function gets bigger as we go to the right. In this case down here, it's saying as the x gets smaller, as we get closer to negative infinity, that's as far negative numbers you could go, to infinity and beyond, as like Buzz Lightyear would say. As we go farther left, the graph goes farther up, which means it gets positive. So it's a little confusing. Okay, go back through and replay the problem, see if it makes sense, and we're going to try a couple more on the next slide. And this next slide, we have a couple graphs. I want you guys to try these on your own, okay, and then play them when you're ready. So the first one, here's the graph of g of x equals negative 2x cubed minus 3x squared plus 4x plus 2. Okay? So we are going to write this out in function notation. As x approaches positive infinity, f of x does what? We're going to fill in this blank. And as x approaches negative infinity, f of x, that's just a comma there, does what? Your answers are either going to be positive infinity or negative infinity. So as x approaches positive infinity, so as x goes to the right, so we trace the graph. As x goes to the right, what's happening with this graph? It's going up or down the farther out we go. Kind of went up for a bit, but the arrowhead is showing the farther we go, it's going down. So if we're going down, I hope you said it was negative infinity. As x approaches the left infinity, or negative infinity, what is the function doing? So let's go to the left from the middle of the graph. It went kind of down, and then it cycled back up, didn't it? When we kind of trace it out. If it's going up, that's positive infinity. So this is the notation you're going to be using. As x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches positive infinity. I want you guys to try this one. And sometimes in your book they may even switch it. They may say f of x approaches negative infinity as x approaches positive infinity. F of x is talking about the up and down. X is talking about the left or right. Just keep that in mind. Okay, so if you haven't tried the bottom one down here, this graph, go ahead and try it on your own. It's very similar to the first example. We're going to revert back to example A. Okay, so we start out, we say as x approaches positive infinity, what is the function doing? What is f of x approaching? Positive infinity, that's for x, that's to the right. As we go farther right and trace the graph goes up in the upward direction. So if it's going up, we're going towards positive infinity. If we look at what the function is doing as x gets smaller, as x goes to the left is negative numbers. As we go trace the graph to the left, the graph is generally going up. So we say it's going to positive infinity. So this is end behavior. We're describing what the function is doing. If we could go out to the end of the graph, which with these arrowheads on the end, that means you can't. It goes on forever in that direction. But theoretically, if we can go to the end of the graph, what would happen? We'd be a really big positive number, in this case, both to the left and to the right. So let's review what our targets were for today. After this lesson, I hope you are now able to determine whether or not an equation is a polynomial and write it in standard form. Use synthetic substitution to evaluate a polynomial function for a given value. Describe the end behavior of a graph of a polynomial function, and graph a polynomial function with the assistance of a graphing calculator. So all those things are very important. Things you're going to be tested on not only in this class, but outside of this class, ACT, MME, all those important exams coming up to you either very soon or next year. So make sure you have all these notes down. Feel free to rewind and go back through them. Have them ready to show me in class tomorrow, and have a good day.